Hello, everyone. So today we're going to be talking about the kinetics of reactions, specifically those performed at an industrial scale. So last time we were mostly talking about thermodynamics, and thermodynamics is going to largely controls the general product distribution and is looking at inherent favorabilities of a reaction. But as I often love pointing out, thermodynamics isn't everything. If it was, diamonds would quickly degrade to make uh, coal because graphite is actually a much more favorable species. However, the rate of reaction is really going to often be the controlling factor. And in an industrial setting, this becomes even more important because, as the old saying goes, time is money. So, what we're going to be focusing in on is what we can do to help control the rate of reaction. And we're typically going to be referring to rate with a uppercase R, which is simply going to be focusing on the moles of product formed per unit time. So one of the important things to note is in this context, rate is going to be a size extensive property. So this will be focusing on how much product is going to be generated at, say, a reactor scale. However, in chemistry, what we typically make use of is a lowercase r rate, which is expressing the production of our product with respect to a normalized quantity. So typical classes of normalized quantity is going to be, say, the amount of catalyst. If I have a catalyst limited reaction, more catalyst I add, the faster the reaction goes. Similarly, you can also normalize it with respect to the amount of reactant I feed in. And in chemistry, we almost exclusively make use of volume of the solution. Thus, we express the moles of A formed instead as the molarity of A formed. But again, the further away you move from chemistry, the more you tend to see these other metrics as they are a little bit more applicable in a real world setting. Now, if we're going to be making use of our examination of rates, one of the other things we have to be very aware of is that the rates of reaction depend highly upon what sort of scale I'm looking at the reaction. And this is going to seriously modify how we try and control how the reaction occurs. And there's three major spatial scales we can examine. The first of which should be the one we're most familiar with, and this is the molecular scale of a reaction. So at this point, I'm just looking at how fast the reaction occurs if I only have, say, a couple of molecules present. So this is essentially a well-ordered or well-behaved system. However, it turns out that most systems have a lot more factors controlling the rate. So at this point, we need to scale up to look at a local scale. So this is still a small scale reaction, and is typically the scale of reaction that you've mostly worked at in a chemistry lab of solutions of less than about a liter. Typically, you're going to see a lot of well-behaved reactions on the order of about 100 milliliters. However, if we get much larger than a liter, so I'm working at the kilogram scale or larger, a lot more features can start popping up and really control the behavior of our systems. And at this point, we reach what's called a global scale or global limitations on our kinetics. So we're going to walk through these scales and look at what sort of controls we can have on the rate of a reaction and where they kind of emerge. So we're going to start with the most familiar metric, which is the molecular scale. So on a molecular scale, our systems will be fairly well behaved, and the rate of reaction can generally be predicted based on a rate constant, which should be a temperature dependent property, and the concentrations of each of our reactants and occasionally products, because it turns out that some reactions are product limited, as we can have a fair amount of back reactions slowing down our case. So while we're typically used to seeing, say, the rate of reaction for the production of hydrogen being just dependent upon our two reactant molecules, there may indeed be some great dependence upon the concentration of our two product species. So one of the things to make note of is that real rate equations can actually be very difficult to construct because a lot of the times we're not dealing with the simple elementary reactions that we often imagine in our classic physical chemistry course. Instead, what we often have to deal with is there may be several back reactions, side reactions, and so forth. And oftentimes, rate equations are derived experimentally instead of from first principles based on what we'd expect based on elementary reactions. However, if we're still working at the small molecular scale of elementary reactions, it is often possible to determine our rate constant, which is a major controlling feature, based on transition state theory. And transition state theory helps give us a lot of insight into what sort of controls we may have on the rate of reaction. Because again, the larger the rate constant, the larger the rate of reaction. So looking at these equations, we might be able to come up with a couple of key controls over the microscopic kinetics. And again, microscopic or molecular scale kinetics is almost entirely controlled based on these two equations. So some of our major controls are going to be simply over the nature of the reaction. So is our reaction, say, mononuclear or first order, or is it second order? Second order with regards to how many species. And uh, by knowing this, I might be able to have some control by putting the limitation all on one species or another, or I might be able to set it up in some fashion that I switch from one reaction being limiting to another. So again, this can be quite important. Another key feature is going to be catalytic activity. So catalytic activity generally works by, again, changing the nature of the reaction by changing the nature of the transition state. So it focuses on trying to lower my free energy barrier, which should end up increasing my my rate constant, which again increases the rate of the reaction. The classic control is again going to be on species abundance. Good old Le Chatelier. The more of the reactants I put in, the faster the rate. However, there is another major key feature of reaction control, and that's actually the temperature. So this is one we talk about a fair bit of in physical chemistry because temperature essentially has two features. The higher the temperature, first of all, the lower the effective energy barrier. So this term essentially goes down, with the negative coefficient, that ends up resulting in an increased rate of reaction. Because more or less I have more molecules with an energy sufficient to surpass the barrier. But we also see essentially the molecules coming into contact at a faster rate, which is where this extra prefactor plays a role. And as a general rule, you can imagine as we increase the temperature by about 10 degrees, we tend to double the rate of reaction. However, that exact relationship is highly dependent upon what temperature regime we're looking at and the exact free energy barrier. Now, one of the things that we actually have to watch out for is that all of these properties aren't necessarily fixed. So as the reaction proceeds, we can start running into some serious problems. First of which is that I'll often start depleting my reactants, and so the reaction tends to slow down. One of the quick solutions is to keep pumping in reactant at a steady rate to keep the at a steady rate in order to keep the actual rate of reaction relatively constant, which again we do love as it offers a way to maintain steady state. Another major feature you have to watch out for is, again, going to be related to this temperature. Because what we need to first determine is my reaction exothermic or endothermic. If my reaction is endothermic, I'm going to be watching my temperature decrease as the reaction proceeds, which is going to ensure a slower rate the longer the system sits. This can often be solved by adding in by adding in a heating unit to maintain the temperature. But a more insidious option is going to be if the reaction is exothermic, because the more exothermic the reaction is, as the reaction goes faster, the, as the reaction proceeds, I'm going to generate a higher temperature via the heat of reaction. As the temperature goes up, the reaction will end up speeding up again, which is going to ensure that the reaction produces more heat, which speeds up the reaction, which produces more heat. This can quickly reach what's called runaway conditions, and is one of the reasons why temperature control and heat exchangers are play such a crucial role in industrial chemistry, as we need to make sure to try and avoid runaway conditions as much as possible. However, this is all simply looking at what happens on a molecular scale. But in reality, there's a lot more things we have to worry about, especially as we move away from simple homogeneous reactions that we love talking about in chemistry. So as I scale up to the milliliter to low liter scale, I need to start accounting for several other key features. The first of which is going to be the rate at which species come into contact, because it turns out a lot of processes are diffusion limited. You may end up with a reaction that has a very low delta G, but I may have a fairly low concentration. So the reaction will essentially occur at the rate at which two molecules come into contact. And this can and there's many ways we can try and speed up these reactions. A classic option is simply making sure that our solution is well mixed to encourage collisions happening as frequently as possible. Another major feature we have to watch out for occurs specifically in catalyzed chemistry. So for example, I may have a solid reactant or a solid catalyst. And it turns out the rate of reaction is going to be entirely based on the surface area of my catalyst instead of its mass or concentration. A classic example has been occurring in a lot of metal, surface metal catalyzed systems, where I may have, say, something like this case, where oxygen and carbon monoxide can combine to form CO2. Well, it turns out that in order for this reaction to occur, they need to make contact with a gold surface, which poses a slight problem. If I put in a large lump of gold, I'm going to have very little surface. But if I put in a lot of very small specks of gold, I've drastically increased the surface area per mass of gold used. It turns out this is one of the major advantages of using nanoparticles, because the smaller the system is, the larger percentage of that material is present as surface area instead of as internal area. And it turns out that very much related to this is I may have a catalyst or a surface that may have its sites blocked by another material, such as carbon monoxide. And this is a classic problem in a lot of biochemistry, as you may end up having an active site blocked by another material. So even though there is plenty of sites technically available, most of them may not be present for reaction. And for this case, you often have to worry about things like carbon monoxide and amines, which love to bind to surfaces, as well as the classic threat of oxidation. One of the other very important things you have to watch out for is that it turns out not all species are created equal. So let's say I do have a gold, in this case of gold catalyzed carbon monoxide oxidation, I may have a lot of gold surface. But it turns out that in a lot of these surface catalyzed reactions, almost all of the reaction occurs at edge or defect sites. So for example, in this case, I need both gold and titanium oxide to be present to allow for the reaction. This generates essentially a polarized oxygen-oxygen bond for my carbon monoxide to react with. In addition, you may end up having a gold surface where I have one face and then another corner face. And at this corner site, that's where you're going to have the most open sites for coordination. So again, edge, edge and defect sites where things aren't perfect, and my metal often has um, open open coordination sites can really help increase the rates of reaction. And again, finally, we do have the classic threat of competing reactions. There may be some other reaction consuming my products or my reactants. And for example, we saw a lot of this come into play when we were talking about combustion reactions. If I don't have enough oxygen, I may end up generating the wrong material. And again, a lot of this is occurring not so much on the scale of the elementary reactions, but what happens when I have to tie a lot of reactions together for a complete reaction chain. And again, related to this is I may have uh, uh, catalytic or surface sites becoming blocked by some of these unintended products. So a lot of these features are things that we kind of ignore or take for granted when we're looking more at a perfect homogeneous system, because you'll notice that most of these tend to be a little bit more exclusive for the use of catalyst or or solid state materials, which, however, due to their ease of separating these materials, are quite popular in industrial chemistry. Finally, we have to watch out for what may end up happening at a global scale. So once I get to about a liter or more, then I have to watch out for a lot of other assumptions that break down. For example, we're typically assuming that all of our reactions are going to be at a single temperature. But we also saw that things like mass and energy transfer can cause hot pockets or low pockets, high pockets of temperature or cold pockets, especially those occurring near a cooled wall. And similarly, we may end up running into pockets of high or low concentration. This most classically occurs when you're making use of a catalyst, where you may end up with a zone of depleted reactants near the catalytic surface, and this can greatly slow down the reaction. So then the real question is, how do we treat these phenomena? So practically, we often make use of trying to mix our solutions as well as well as trying to do our best to model temperature transfer within a system. But practically, in terms of trying to figure out their influence on rates, the, mo- um, the most uh, the best approach is just simple, rigorous experimental testing. Because once I scale up to a kilogram or larger scale, there often becomes so many competing phenomena that I actually have to test the system to be sure of what the heat production rates are, as well as the relative species abundance throughout my entire mixture. Again, another option is going to be trying to figure out what the average behavior is by, again, experimental measurements, and then try and come up with a model based on mass and heat transfer to figure out what the typical deviation from that average is. And then the last option, which is becoming increasingly popular, is to build an extensive computer model. Again, the detail of the model is often dependent upon how much time you have, but again, often requires a lot of data about what's happening at the molecular or local scale to inform a true global scale model. That brings us to the end of our overview of kinetics. Next time, we're going to be talking about how some of these kinetic issues can be treated when looking at actual chemical reactors, and how we can essentially try and fight some of these deviations from ideality. Till then, take care.